So I'm going to talk a little bit about the basics of combustion, and we'll start off with the simple fire triangle, which some of you may be familiar with, which is for combustion to take place you need three elements. You need fuel to burn, but the fuel will not burn until it meets oxygen. So fuel and oxygen are the reactants that cause the combustion process. But the combustion process will not take place unless there is some method to ignite it. So you can have fuel and oxygen sitting around in an atmosphere with no ignition source and it will not combust. So the third part of the triangle is heat, which can be temperature, hot surfaces, or some kind of spark ignition, or even the sun. So as I go through this preliminary presentation on basics of combustion, I'm going to be highlighting a few definitions which hopefully will be useful as we get through this later on. So combustion is a chemical reaction in which fuel undergoes oxidation. This is an exothermic reaction, as in heat is released, and for most of the people who are attending this webinar, you'll be involved in processes which are converting a feed to a product, and that process requires heat to drive it from the feed to the product. That reaction will be an endothermic reaction, one that absorbs heat, and the heat that is required to make that process happen is provided by the combustion within the kiln. Within the kiln, the conservation of mass and energy remains, so that a mass or energy is neither created or destroyed, which is important when you're looking at an overall balance within the kiln. So if I simplify the basic chemistry of combustion to a hydrocarbon, and the simplest hydrocarbon is methane, which most of you will be aware is CH4. Once you know the fuel, you can derive how much oxygen is required to convert the carbon, I get my arrow working, carbon to CO2 and the hydrogen to water, which is actually in its gaseous state as vapor. Obviously the oxygen comes when it's mixed as part of air with some nitrogen, and that's carried over through. So there's conservation of mass, there's one carbon in the feed, there's four hydrogens in the feed, there's four oxygens, two there and two there. So conservation of mass is maintained. And this process is exothermic, and the process releases energy. Stoichiometric is a term used to assess the actual ratio of fuel and air. So a mixture that has exactly the right amount of fuel and air to perform perfect combustion. So in this previous case, taking methane and converting it to CO2 and steam, that would be called a stoichiometric mix, and there's no unused fuel or air. Equivalence ratio is used to quantify the ratio of air to the fuel in the mixture. So at stoichiometry, the equivalence ratio is 1. If you hear of an equivalence ratio greater than 1, it means there's some excess air available. Continuing definitions, most of you may be familiar with the term heating value or higher heating value, gross heating values. These are terms which are used to assess the amount of heat which is released from the fuel, taking into account heat available from water from the combustion project. So this in the previous case would take methane and oxygen and convert them to CO2 and water in its liquid form, referenced to 60 degrees Fahrenheit. Now in reality, that higher heating value is not released, and the net or lower heating value is what we use and see within inside the combustion process. So it's the usable heat from combustion where products exit the process before they condense to water, hence that comes out as a water vapor, and effectively there is heat lost in retaining the gas in its water vapor form. So this is really the energy which is available to the process within the kiln operation. Dry and wet products of combustion are compared. Dry is without the water vapor, wet is with the water vapor. So if you're looking in a kiln and measuring the oxygen, at the back of the kiln you will see the water vapor. So the O2 will reflect the gases coming out the kiln and include water vapor. If you're measuring with some external device where the water is condensed, such as a handheld portable or a stack analyzer, you'll be measuring a dry O2, which does not include water vapor. And so you can see that the oxygen measured dry is going to be larger than the oxygen measured wet because it doesn't include the water vapor. The dry volume is obviously less than the water vapor with the wet volume. Upper explosion limits and lower explosion limits. These define the percentages of fuel and air mixture that once ignited propagates self-sustained flame. So what this means is if you're within the flammability limits, i.e. you're above the lower explosion limit or you below the upper explosion limit, you have a fuel and air mixture which can be ignited and will continue to burn so long as there's fuel and oxygen available. If you are too air rich, that means you're below the lower explosion limit, you're too lean, and what happens is that the flame will go out once your ignition source is removed. At the upper limit, you've got too much fuel, and the same thing applies. So there is a bound for each fuel and air where there is a mixture which maintains and sustains combustion. Now, industrial systems are non-ideal, and so we have to take this into account when looking at the previous definitions and theories. Combustion of any typical fuel involves tens or hundreds of intermediate reactions in species, free radicals and various intermediate reactions that are taking place. Real combustion requires more than theoretical air requirements, the SAR, and so most operations that you'll be exposed to will run with a little bit of oxygen at the back to ensure that all the fuel is combusted and is consumed within the kiln operation, and there's just a little bit of spare air coming out on top. Not ideal combustion, and when you're using difficult fuels, can result in reactions not going to completion. This is when the combustion hasn't gone all the way through to CO2, and it's often experienced through measurements of CO, carbon monoxide, at the back end of the kiln operation. CO formation is asymptotic, it rises quickly, and it requires a high temperature and oxygen available to burn through to CO2, carbon dioxide. So that once it forms in the operation, even though there may be some O2 available further on, if the temperature is not sufficiently high, it will remain as carbon monoxide. Other products that we'll talk about are NOx and SO2 will not be covered in this particular presentation. Adiabatic flame temperature. Those who've been involved in combustion will have heard this term before. It is the theoretical flame temperature which arises at stoichiometric conditions where there's no spare oxygen, there's just the amount of fuel available with the oxygen to burn through to combustion products, primarily steam and CO2. It's surprising that there is a fairly tight range for most industrial fuels, so natural gas versus coal. In terms of its adiabatic flame temperature, it's relatively similar, and if you compare those numbers to an oxyacetylene flame for welding, you'll see they're actually quite modest. Factors which impact the adiabatic flame temperature include the equivalence ratio. So you'll see we talked about it being perfectly stoichiometric at 1, and you'll see that the peak temperature is slightly on the air-rich side of the fuel equivalence ratio. This is because you're ensuring that all the CO is combusted to CO2, and so you just have a little bit of oxygen extra to make sure that takes place. But you'll see as you move either side of the equivalence ratio, the temperature drops quite dramatically. Now, I won't be talking much about heat transfer, particularly in this presentation. Perhaps that will be part of a further presentation. What I would say is that heat transfer is a function of temperatures within the kiln, and so getting the highest temperature enhances the heat transfer within the kiln. Other impacts on flame temperature are air temperature, surrounding air temperature, and this is a kind of extreme graph, but I've kept it in Fahrenheit just to keep it relevant to the audience here. And so you can see that temperature in the 3,500 to 3,700 can rise quite considerably if you're preheating the air that's moving in. So the use of product coolers to capture heat from the product and take it back into the kiln does accentuate the adiabatic flame temperatures within the kiln, the flame temperatures for heat release and heat transfer, and so you'll elevate those temperatures and enhance the heat transfer within the kiln. So these always help. Combustion of pure oxygen also increases flame temperatures, so some people in the audience will have been involved with oxygen injection to a kiln, and what you're actually experiencing is this reaction without the nitrogen. So you're doing the same reaction, but we don't have the energy heating up the spare nitrogen to flame temperatures, and so the whole thing gets a lot hotter. And as you can see, we're talking here down to 3,000, mid 3,000s, it rapidly rises. So significant steps can be made to the flame temperature by adding oxygen, and in fact up to obviously 100% oxygen. Further definitions: auto-ignition temperature, or sometimes referred to as the kindling point, is the lowest temperature where spontaneous ignition will take place. So this is a situation where you have fuel and air in a place somewhere, and it's hot enough that it just ignites without a spark, sunlight, whatever. It just takes off. That's called the auto-ignition temperature, and it's basically provided with the sufficient activation energy to initiate combustion. It's relatively high for gases compared to solid fuels and liquids, and it is used, and some of you may be using it already, within the NFPA flame detector bypass, which allows proving, which says that if the temperature is over 1400 degrees F detected within the kiln, you don't need flame detectors. It's assumed to be combusting because it's so hot, it's above the auto-ignition temperature. And this can be very helpful in operations where you have a very dusty environment. Heat energy is in transit. It's stored as heat and increases the temperature. So you start off with the original fuels, and effectively the heat is stored within those fuels until they react, passing the heat into the atmosphere around it. If you were to put 100 BTUs into a pound of water, its temperature would rise by 100 degrees F, and its volume would increase by 2.2%. But if you put it into air, it will rise by 400 degrees, and its volume will increase by 62%. And some of this expansion is the work that's used to generate the heat transfer within the kiln.